Welcome to another video in the Sunrise series, showcasing the outcomes of Use Case 3.2, Highway Automated Driving Validation, Cooperative Perception, Decision-Making, and Control. Sub-Use Case 3.2-C1, Cut in on the ego's lane, careless merge. In this video, we test an automated driving system, ADS, equipped with V2V communication. We assess how the system responds to communicated careless merging on highways, evaluating its ability to avoid collisions. 5 parts of the SAF will be demonstrated, namely concretize, execute, test, evaluate, coverage, and some steps of the safety case building. The test case setup is based on simulations carried out in IPG CarMaker. 3 systems under test are examined: a cognitive self-driving agent, a traditional path planner, and a generalized intelligent driver model, GIDM. The scenario is a highway. The ADS travels on the right lane. Suddenly, it receives a message from a vehicle on the left lane that it is going to cut in. Apart from communicating the lane change path, the car on the left maneuvers without waiting for ego approval. The burden of avoiding collision stands entirely on the ego, sub-use case C1. The goal is to evaluate the conditions under which the system can avoid collisions and utilize this information to improve its behavior. We followed a safety argumentation checklist that covered a microscopic evaluation of results for individual scenarios, a macroscopic evaluation by aggregating the results into a surrogate model, and the use of that model to create safe speed recommendations. Key artifacts include coverage of the scenario space with a surrogate model that provides confidence levels, evaluation of risk scenarios, and determination of the safe speed. We will show these steps. Concretize. Human experts defined a 5-dimensional logical scenario, which was concretized into 5,000 initial points. Execute. The 5,000 concrete scenarios were simulated in IPG CarMaker. Test, evaluate. Concrete scenarios were classified into 3 categories: collision, C; near miss, N; or safe, S. Other surrogate ancillary metrics were also collected. Test, evaluate. A surrogate model was trained, which provides fast predictions with confidence levels. Coverage. The model was validated on 1613 new independent concrete scenarios. Safety case. The model was used to evaluate the risk for 3 types of cut-in. Safety case. The model was used to discover failure modes. Safety case. The model was inverted into a safe speed recommendation function. A 5-dimensional logical scenario was defined by human experts, taking into consideration the ALKS regulation and the scientific literature. It was concretized into 5,000 initial random points. The scenario parameters are 5: the vehicle's and obstacle's velocities, the obstacle's distance, the obstacle's deceleration, and the lane change duration. In CarMaker, 5,000 simulations were executed, taking a full day on a desktop computer. A successful evasion is shown at the top and a collision at the bottom. This video shows a successful evasion. This video shows a collision. Concrete scenarios are classified as follows, based on position and relative velocity at collision, or the nearest position if no crash occurred. Collision, C. The ego vehicle could not avoid a collision. Near miss, N. Close flyby as shown below. Safe, S. None of the above. The nearest position of the obstacle for the 3 classes is shown below. A surrogate predictive model was constructed using bootstrapping aggregation. Details of the method are provided in the linked paper, as follows. 100 independent neural network predictors were used. It is akin to 100 independent judges predicting any scenario within the logical parameter ranges. The number of judges that agree provides confidence in a prediction. The figure below shows an example of the confidence level for collisions. The classifier model was tested on 1613 new random sample points. By setting the confidence level to 99.5%, requiring all 100 judges to agree that the situation is safe, the model achieves nearly 100% recall, with no collision cases missed. 3 risks are evaluated. 1. A naturalistic driving lane change of a vehicle moving faster than the ego. 2. A naturalistic driving lane change of a vehicle moving slower than the ego. 3. An extreme lane change of a vehicle moving faster than the ego. 2 ADSs are assessed below, presenting the predicted collision rate at 2 confidence levels. The cut-in of decelerating or slow vehicles is the most critical case. At the center, the surrogate model was used to generate 200 points near the boundary of the collision regions. They were simulated, resulting in 57 near-miss cases clustered into 19 different types. 6 are shown. For example, Cluster 9 collects cases where the ego avoids colliding with a braking obstacle by swerving left. The surrogate model was inverted to establish when the speed becomes unsafe in the case of a cut-in. The example below refers to the crash depicted on the left, which occurs when the ego velocity is 20 meters per second. However, the ego would be safe if it remained below 18.1 meters per second, as indicated on the right, assuming a naturalistic driving lane change. In this video, we have shown expert-defined logical scenario. Test results are aggregated into a model that predicts confidence levels. Testing prediction recall across the logical scenario with an independent test set. Evaluation of 3 types of risks using the validated model. Identifying failure modes at the edge of the collision area. Inverting the safe region to determine the safe speed. Concerning limitations and future work, the following comments apply. Human intervention is required to adapt the method to different logical scenarios. Human intervention is necessary to interpret the results. Automating the process may be necessary for optimizing the surrogate model hyperparameters.